This is a talk on my joint work with Paata Ivanisvili on learning polynomials on the discrete hypercube that will be presented in STOC. Now, before I move on to the main subject of the talk, which is learning, let me start with a crash course on analysis of the discrete cube. So the discrete cube is the set plus minus 1 to the n, so it's a discrete set, contains 2 to the n points, and we are studying functions defined in the cube with values in the real line. Now, the cube is a finite abelian group, so of course, everything can be expanded, every function on the cube can be expanded on a basis of characters, and it has 2 to the n points, so therefore it has 2 to the n characters, which are these functions here, ws, which are called the Walls functions, and are indexed by the 2 to the n subsets of the set 1 to n. So every function in the cube can be written as a sum over those 2 to the n subsets, some Fourier coefficient times the corresponding character, and Walls s at a vector x is just the product of the coordinates I in S of xi. So it's very simple to see that these are pairwise orthogonal, and therefore they actually span the space of functions on the discrete cube. Now, since these are orthogonal, they are an orthogonal basis, we have a very simple formula for the Fourier coefficients. Since this is coming from an inner product, the Fourier coefficient is the expectation of the function f times Walls s, where always when I write expectation in this talk is going to be with respect to the uniform measure. And you see that these functions Walls s are actually monomials. So this tells us that every function of the cube can be expanded as a polynomial, which, if you're careful, you would have observed that this is a multilinear polynomial. So we don't have any terms of the form xi squared or something like this. So every function in the cube is a multilinear polynomial, and we say that f has degree at most d if all the Fourier coefficients corresponding to subsets, so to monomials of size bigger than d, are equal to 0. Now, in this talk, we will be speaking about learning. So let me introduce the problem. We are given an a priori known class of functions on the discrete cube minus 1, 1 to the n, which I'm going to denote by script f. And we fix now an unknown function in the class. And the game is the following. We are given data of the form x1 of f of x1, x2 f of x2, xq f of xq, where x1, x2, and so on are just now points on the cube. And what we want to do is that we want to algorithmically construct a hypothesis function that well approximates f. So in reality, we are given some values of the function f, and knowing the information that f belongs in the class script f, we want to be able to basically reconstruct the function. And the main question, of course, when you pose a problem like this, in order to make it rigorous, is how are the points, how is the data coming to us? And in this talk, we shall only be interested in the random example model, in which the samples, capital X1, capital X2, etc., are IID random vectors, each uniformly distributed on the discrete hypercube. So in this model, we are given random samples. So at the end, what we want to do is that we want to produce a random function, so a random hypothesis function, little h, which is a good approximation of f with high probability. And the main question, or one of the main questions in this problem, is how many samples do you need? So how small can we take the number capital Q that we had in the previous slide? And just to formalize everything, so I'm going to introduce this notation. So Q sub r, the number of queries, r here stands for random. For the class F, if we want to have an approximation of epsilon with probability 1 minus delta, is the list number such that we can always output a random function h, which is epsilon close to f in L2, so in the L2 distance, with probability at least 1 minus delta, where now this is the probability with respect to the randomly generated data. And the first remark that one should make is that the class of functions that we're given has to have some special structure in order to be able to prove anything meaningful. For instance, if we consider this class script f, which is the class of all functions on the hypercube, which take the values 0 and 1, then one needs at least 1 minus epsilon times 2 to the n values in order to make an accurate hypothesis for a function f in this class. And why is that? If you know 1 minus epsilon 2 to the n values of a function f, then there is still an oscillation of epsilon for all the other values. So you need to know more value than that in order to make an accurate guess. And some structure is needed, and structure is encoded by what we would call low complexity of the class. And there are many reasonable notions of complexity, but one class which is somehow undoubtedly has a property like this is the class of polynomials. So the first class that was studied for this problem basically is this class f sub n comma d, which are all the functions on the hypercube which take values between -1 and 1 and have degree in the notion of the first slide smaller than d. So d here is a number between 0 and n. And notice that we have this normalization that f is actually bounded by 1 in the L infinity norm. That's a normalizing condition, but it is actually important to have some kind of normalization because you know there's a choice of scale with this parameter epsilon. And later in the talk, we're going to see that actually the L infinity normalization, rather than something weaker like L2, is very important for the results that we present. And now, of course, what's the idea behind the study of this class is that polynomials can be reconstructed from very few values, and that's true even in the real line. So, you know, if you have a degree d polynomial on the real line and you know d plus 1 of its values, then you can completely reconstruct it. And this class was first studied in 1989 in one of the somehow pioneering works in computational learning theory, which is the low-degree algorithm of Lineal, Mansour, and Nissan. And what they proved is that the query complexity of the model, so a polynomial in this class can be learned up to error epsilon with probability 1 minus delta in what is roughly n to the d times log n samples. I should say the main enemy in this talk is the dimension n rather than epsilon delta or the degree d. Okay, so Lineal, Mansour, and Nissan proved that you can learn a polynomial in n to the d log n samples, and I'm going to show you the proof of this statement, even though many of you may know it, just because it will be instructive for the results which will follow. So this is basically an application of concentrational measure, and the idea is actually quite simple. So, you know, we have this class of polynomials which is defined spectrally, so we know that some Fourier coefficients are equal to 0. So what we're going to do is that we are going to create a spectral approximation of the unknown function f, basically by trying to learn each individual non-zero Fourier coefficient separately. Okay, so fix a large number q and take x1 up to xq IID random samples. And now for a subset of cardinality smaller than d, what we're going to do is that we're going to replace the actual Fourier coefficient, which, as we said, is the expectation of f times Walls S, by the empirical Fourier coefficient. Okay, so this is the expectation of f times Walsh, but not with respect to the uniform measure, since we don't know f on the whole cube, but with respect to the empirical distribution. Okay, so this here is an average or sum of bounded independent random variables, the expectation of each of which is equal to the Fourier coefficient. Now, the boundedness here comes from the fact that f was bounded by one absolute value. And therefore, one can apply the Chernoff bound to see how far the empirical Fourier coefficient alpha s is from its expectation. And so we get that the probability that alpha s minus f hat of s is bound below by b is satisfies a Gaussian theorem, basically. It's bound above by 2e to the minus q, which was the number of samples, b squared over 2. So if q is massive, then morally the two coincide. And we can also apply the union bound and say that, well, if we want alpha s to be close now to f hat of s for every subset of cardinality at most d, then this is the probability of the complement, so it's bounded below by 1 minus this number, sum j goes from 0 to d of n choose j, which is the number of subsets, times the Gaussian tail, 2e to the minus qb squared over 2. And now this probability is bounded below by 1 minus delta if q has this value here. So for this value of q, this probability is bounded below by 1 minus delta. And now, so what have we done? We have guaranteed that if q is this big, then all the Fourier coefficients are close, or the empirical Fourier coefficients are close to the actual Fourier coefficients. And now the name of the game is the following: we have to choose b which is small enough so that this condition guarantees that the empirical function is close to the actual function, and still large enough so that this number q is not huge. Okay, so what we have to do is to estimate the L2 norm. So of course our guess is going to be the function which is the sum of the empirical Fourier coefficient times Walsh rather than the actual Fourier coefficient. And if we want to estimate the difference between f and this empirical function, by Parseval's formula, it's a sum over all subsets of the Fourier coefficients of the difference squared. And now each of those numbers is bounded above by b squared, just because we are in the high probability band. And there is this number of them, sum j goes from 0 to d n just j. And this is smaller than epsilon if we choose b squared to be smaller than epsilon times this sum. Okay, so morally b squared is epsilon over n to the d. And now if we go back to the formula for q and plug in b squared equals epsilon over n to the d, we get the n to the d log n that we have. And that's the end of the proof. This is the low degree algorithm. It's a very beautiful theorem, classical too. And the question that we are going to address is, are n to the d log n samples too many? And the first advance in this problem since 1999 was in a very nice paper last year by this set of authors, Ayer, Rao, Rice, Rothfuss, and Yehudayev, who showed that in fact n to the d log n can be replaced by n to the d minus 1 log n. Okay, so this may seem like a modest increase, but in reality, it breaks the conceptual barrier because n to the d log n is really the dimension of the space times log of the dimension of the space. And this actually has a conceptual meaning. And this is the first result which shows that you can actually do a bit better. Now, the main theorem of this talk is that we can actually very much improve over this result. And the real answer, which we were able to prove last year, is that, in fact, the query complexity is bounded above by log n up to constants depending on d epsilon. Now, this is not the subject of this talk, but I just want to say that in more recent work with Ivanisvili and Lauritz-Feck, we were able to also prove the matching lower bound. So in fact, log n is the correct number of queries for this problem. Now, for the rest of the talk, I'm going to discuss the proof of the log n upper bound. And to do this, let's just examine where we lost in the proof of the low degree algorithm. So notice that, f is bounded in L infinity, so in particular, it's also bounded in L2, which by Parseval means that the sum of the Fourier coefficient squared is bounded by 1. And there are roughly n to the d Fourier coefficients. Okay, so if we want to choose our number b squared to be substantially bigger than n to the minus d, as we would in order to get a smaller value for q, a lot of those Fourier coefficients would actually be substantially smaller than b squared. So in a way, incorporating all of them in the hypothesis function is a major weight because we're introducing a larger error than the size of the actual quantities. So what we want to do is just keep the ones which are influential, keep the ones which are reasonably large. And if we want to see how many Fourier coefficients are larger than, let's say, a parameter a, then we can apply Markov's inequality and say that their number is boundable by 1 over a squared times the sum over those Fourier coefficients. And now this sum is bound, of course, above by the sum over all Fourier coefficients, so f hat of s squared, which we just saw is bound above by 1 by Parseval. And therefore, if we make this guess, what we are stuck with is the need to estimate a sum of this form. So we have to take the sum over those Fourier coefficients which are small, so smaller than a, of f hat of s squared, and we want to argue that this is smaller than a parameter epsilon of a, which goes to 0 as a goes to 0, of course, ideally in a dimension-free way. Okay, so it leads us to understand the kind of weak inequality of this form, and also just by this reasoning, you immediately see the need to have an L infinity bound rather than an L2 bound. Because if we were to choose, even for d equals 1, all the Fourier coefficients to be 1 over square root of n, then for any constant value of a, this sum here of the Fourier coefficients which are smaller than a would simply be equal to 1. Okay, so if you had the function x1 plus x2 plus xn over square root of n. So the boundedness actually has to play some kind of role in order to get this weak estimate here. And the tool which is gonna let us do it is a classical tool from approximation theory, which I have to introduce now. So let me start with the triviality. If you have real numbers, a1, a2, etc., then the sum of their absolute values is the supremum of some ai xi, where x is a bounded vector in L infinity. Okay, of course, the optimal x is just choosing the sign of the ai. So what I just said is a triviality here. Now, Littlewood, in a very famous work in 1930, answering a question of P.J. Daniel, extended this, or actually found the correct analog of this property for bilinear forms rather than linear forms. So if you take numbers aij, where I and j are again greater than or equal to 1, so notice that I'm speaking about infinitely many i's and j's, so that I want to emphasize that this is a dimension-free inequality. And you look at the supremum of the bilinear form aij xi yj, where x and y are now points which are bounded at infinity. This is, of course, bounded above by the little L1 norm of the aij's, by the triangle inequality. That's trivial. But Littlewood's inequality tells us that it's bounded below by a different little LP norm, where the p is equal to 4/3. And there's this constant square root of 2, which is independent of everything. And what's amazing is that the exponent 4/3 and the constant square root of 2, which was actually proven more recently, are both sharp. Okay, so this is a reversal, in a way, of the triangle inequality for this kind of bilinear form, but you are forced to take a different exponent rather than one. And of course, there's nothing special about degree 2 or bilinear forms. This is a general statement about polynomials, which was proven a year later, a year after Littlewood, which is the Bonin-Gostila inequality, which says that for a degree d polynomial of this form, sum c alpha x to the alpha. Now, alpha is a multi-index, and the polynomial may in principle depend on infinitely many variables. The sum of the coefficients to this power 2d over d plus 1, all this raised to the power d plus 1 over 2d, is bound by some constant which depends only on d and not the number of variables, times the supremum of the polynomial over vectors x, which have an infinity norm bounded by 1. Okay, so this is a classical inequality in approximation theory. And just to mention the connection, suppose that P is in fact, rather than a general polynomial, it's actually a multilinear polynomial, which represents a function on the hypercube. Then, since it's a multilinear polynomial, its supremum over the solid cube is actually attained in one of the vertices. And therefore, this inequality here is really an inequality which applies to polynomials on the hypercube. So if you have a degree d function on the hypercube, what we get is that the sum of f hat of s to the power 2d over d plus 1, and this all raised to d plus 1 over 2d, is bound above by some constant, which I'm going to denote by bd now, because when there is some difference between this constant and this constant, even though one is smaller than the other, times the L infinity norm of the function. Okay, so this is an inequality which genuinely holds true on the Hamming cube by these very classical things in approximations. And using this, let me just show you how to prove the logarithmic upper bound for the queries. Now, this idea goes back to Koshilevich and Mansour of introducing a cutoff in the spectrum. So again, we fix B positive, we have the same number Q, and we know that with probability 1 minus delta, all the Fourier coefficients are close to the empirical Fourier coefficients up to an error of B. That's exactly the same as in the previous proof. Now, the new thing which we're going to do is that we are going to consider the random collection of sets of all subsets for which the empirical Fourier coefficient is bounded below by 2 times B. Okay, so this is an empirical quantity, right? So we know all the empirical Fourier coefficient. What we do is that we isolate the ones which are bigger than 2 times B. And notice that if we are in the high probability event, so if we are in the high probability event, the real Fourier coefficient and the empirical one are just B apart. So if we are in sigma B, which means that alpha s is bigger than 2b, then f hat of s is bigger than b. If we are not in sigma B, which means that alpha of s is bounded above by 2 times b, then also the real Fourier coefficient of hat of s is going to be bounded above by 3 times b. And now our guess is going to be the function, which is not the sum over all subsets, but the sum over the significant subsets, the ones in sigma b, of the empirical Fourier coefficient times Walsh. And now when we estimate the L2 difference between f and this empirical function, it's the sum on the important subsets of the sum of the difference of Fourier coefficients and the sum on the unimportant subsets of just f hat of s squared. And what the idea that we said before is that the first sum is over very few subsets, and for whichever reason the second sum has to satisfy some kind of weak inequality which is going to make it strong. Okay, so just make those things rigorous, starting by the first one. So for the first one, let's just see how many terms are in the first sum, and we are going to estimate this by Markov's inequality, but using Bonham-Lustile. So as we said on sigma b, the Fourier coefficients are greater than b. So the cardinality of sigma b is bounded above by b to the minus this power, 2d over d plus 1, times the sum over all s in sigma b, f hat of s raised to the same power, 2d over d plus 1. But this can be bounded above by the sum of all Fourier coefficients to this power, and this is just bound above by this constant bd to the 2d over d plus 1 by the Bonham-Lustile. Okay, so the first sum does not contain many terms, and therefore we can bound each of them from above by b squared, and there is this many of them. So if you combine those two, the first sum is bound above by this constant which depends only on b, times the little number little b raised to the power 2 minus 2d over d plus 1, which is just 2 over d plus 1. So we did take care of the first term. Let's take care of the second term. Now the second term, we are summing over the subsets which correspond to small Fourier coefficients. Okay, so each of the Fourier coefficients here on the second sum is bound above by 3 times b. Okay, so we have the sum s not in sigma b of f hat of s squared, and for each of them we are going to take out a small power 2 over d plus 1 and bound the corresponding Fourier coefficient by 3 times b. So we have 3 times b to the 2 over d plus 1 times the sum of those Fourier coefficients to this power, which again is bound above by 3 times this constant which depends only on d times b to the 2 over d plus 1. And now if we combine the two, we get that the difference from f to the empirical function is bound by 4, a constant depending only on d, times b to the 2 over d plus 1. And we can make this smaller than epsilon if we choose b squared in this way. Epsilon to the d plus 1 divided by a constant which depends on d. And now if you go back to the value of q and you plug this in, you see that the contribution here of b squared only depends on d and epsilon, and therefore the only dependence on n is coming from the union bound and it's inside the logarithm. So this is a constant depending on d epsilon times log of n over delta. And that's the end of the proof. So I just showed you the proof of this log and upper bound. As I said, there is a matching log and lower bound. Just to be a bit more precise, so the upper bound that we showed is this. So the Bonham-Lustile constant, the power 2d over epsilon to d plus 1. The lower bound has a factor 2 to the d for n large enough, and this appeared in this newer work. And I should say that the conjecture is that BD behaves polynomially. So with the correct dependence of BD on D, we would have an almost matching behavior of the upper and lower bound in terms of D. The best current bound is this, e to the square root of d log d. So now it's something like e to the d to the 3/2. But modulo this well-believed conjecture in approximation theory, you get an almost correct dependence on d. And also I want to say that the dependence on epsilon on the upper bound, which is worse, can be improved to epsilon inverse if we a priori knew that the function was Boolean. That's it. Thank you very much.